Hi, welcome to the Cosmic Pie Podcast. This is episode number 23. I'm your host, Wayne Barkhouse, and here with me today.
And I'm Robert Moore. Nice to meet everybody.
So, Robert, as you know, we are broadcasting live here from the campus of the University of North Dakota in Grand Forks.
Right.
Do you imagine which state are we in again?
North Dakota.
University of North Dakota, so it has to be what state?
South Dakota. No.
I always feel funny because I say we're broadcasting live from the University of North Dakota, from Grand Forks, North Dakota. Where else would you be in, right? What other state, right? Because you're at UND.
Well, I mean, we're awful close to Minnesota.
Well, that's true. We're only, we're walking distance.
Mm-hmm.
So
you don't mind walking.
Exactly. Now, we do have a live chat that's running. So, Robert, if anyone out there would like to send us a chat so we can converse on the topics that we talk about or maybe anything else.
All right. It's right there. We love hearing from you.
Yes, please feel free to use the chat function. Also, just up front here, a disclaimer, anything that Robert and I say are not necessarily the opinion of the university,
right?
Our department, our college, or anybody else.
And it's just us.
Just us. So you can know who to blame in that sense, right?
That's it.
And
that's what it's all about, right?
Exactly.
Who to blame.
And we also thank, of course, our department in the university and the college for letting us do this podcast. Which, by the way, we're coming up to the beginning soon of the fall semester. Here at UND, we start officially on August the 21st at 4 p.m.
Right.
So my first class that I teach would be the following day on August the 22nd. And as far as we can tell, the way our schedules are setting up is that we will be able to continue doing these podcasts on the same day at the same time at 3 p.m. local.
Right.
So far, so good.
So everything's looking good for us not to have to change time on you.
Exactly. Now, one of the things we like to do, of course, is talk about what has happened recently in science. So this is a podcast where we discuss things like physics, astronomy, astrophysics, science in general.
Mm-hmm.
And one of the things we look at, of course, as I mentioned, is things that happened in the recent past. We try to keep it as current as possible, but of course, we're willing to talk about anything.
Right. I mean, sometimes you just want to talk about a background subject. So
yeah, you never know what comes up or what we end up talking about. We go down certain rabbit holes, and you never know where we end up in that sense. Exactly.
I'm late.
Now, one of the things that was announced, this actually happened in late June, if we go to our first slide, Robert, was announcement by the European Southern Observatory, ESO, and what they announced was the fact that a large telescope that they are currently constructing down in Chile. And why Chile? Well, it gives them a good view of the southern sky. And it turns out, I don't know if any of you at all had a chance to go down south, south of the equator. And if you do get a chance to do that, one of the things you'll notice is that at night, at the right time of the year, the center of the Milky Way passes directly overhead.
Right.
So if you want to have a very good view of what's happening in our own home galaxy, that's the place to observe from if you can't get to space.
Right. And like up here in the far north of the United States, the center of the galaxy when it's in the sky is real low on the horizon. So it's very bad for seeing. Another reason to put it in Chile is, of course, the fact that it's very dry there and has a lot of altitude.
Well, yes, so if you go back to the positioning of the center of the Milky Way, so if you're in the northern hemisphere like we are, the best time to look at the center of the Milky Way is in the summertime, like now, and you look towards the southern horizon, towards the constellation Sagittarius. So the center of our Milky Way is in the constellation Sagittarius. And as Robert mentioned, it's very low to the horizon. So you have to look through a lot of that murky atmosphere. So you don't get a crystal clear view like you would if you were down in Chile, where the center would be directly above you.
There you go.
And I have been to Chile several times observing, and I've actually had a chance to go out when there was sort of a break in between to look at the Milky Way, to look at the sky, and it's just unreal what the Milky Way looks like when it's directly overhead of you.
Yep.
In fact, in some sense, some of the dust lanes that go in near the center of the Milky Way, I had the illusion of looking at it in 3D, believe it or not. You have this 3D perspective of that. One of the dust lanes looks like it's projecting out in front of you. And it was pretty awesome sight. I was not prepared to see that. And I was at, a very, very dark location, not too far from where this telescope is being constructed by ESO. And so when you're in a very dark location, it's just unreal what you can see compared to if you're in a place that's, affected by light pollution.
Right.
And that's one of the problems of being in an urban area or even a semi-urban area.
Is
The
light
suburbs
pollution.
is the light pollution.
I mean, if you're looking at this picture, you can even see the nearby city on the left center, that little yellow glow right on the horizon. That's a town, that's a city.
Yeah.
So even where they're putting this, there's light pollution. Over here on the mountains on the right side, you can see one little light on the side of the mountain. So we're getting to a position where
That looks like
right
snow
there.
to me, but from this perspective,
Yeah,
but
it's-
anyways.
Anyway, but yeah, light's beginning to be a problem everywhere on the face of the planet.
Well, there was news recently, it was just a couple months ago, that someone had there's several teams out there looking at the amount of light pollution.
Mhm.
So they got ordinary citizens to use a light meter, a photometer essentially, right? A light collecting device that can measure the ambient light. And from different locations, around the United States and other countries as well around the world. And they estimate that there's a huge increase in the amount of light pollution just over a short time period of roughly 10 years.
Right.
And it's just getting worse and worse and worse.
Yeah.
And so to find places around the world where literally it is so dark you can't see lights from anybody is getting rarer and rarer and rarer.
And I'll point out that even if you're where you can't see light, you're still got a problem with light pollution because it spreads out just like sunlight does to make the sky blue.
Yeah, you have the...
And so you get a background, a sky glow.
Yes, exactly.
Even where you can't see any light, you still have problems with that sky glow.
Now you can go on the internet and look up light pollution map of the United States, for example, and you'll get a graphic, an image of the United States at night showing you that essentially from the Mississippi eastward, it's
all white.
It's all washed out because of lights.
Yeah.
And of course along the western coast through California, Los Angeles, and all that, it's completely wiped out too. There's a few areas through the central part of the country, and of course in the mountain areas, the Rocky Mountains, the Appalachian, along the west coast and the mountains and stuff in the highland areas where there's a lot less lights, of course, because less people live there.
Right.
But most of the United States, eventually it's going to be all light polluted, and it's like, where do you go? You have to go somewhere else, right?
Right.
So this is where you need like a boat and go in the middle of the Atlantic Ocean or somewhere.
And then you got the problem.
Well,
with
then,
the
if you got
motion.
the waves and stuff, it's harder to stabilize your telescope. So,
Right.
Go to space.
Now, I'm going to mention one thing for our American audience. This telescope is going to have a diameter of 39 meters. So that's roughly, it's a little over 40 yards.
Yeah, so just multiply it by 3, and that gives you the number of feet.
So this telescope is going to have a diameter. The telescope, not the dome that houses it. The telescope itself is going to have a diameter roughly half a football field.
So about 120, almost 120 feet across.
Right. So this is how big this thing is going to be. And people go, well, what's good is that going to do with humanity? Well, the engineering feats and marvels that have to go together, come together to build this thing have implications for bridges, for buildings, for other types of buildings, all of that sort of thing. So it has worthwhile, extendable contributions besides just to astronomy.
Now, there's a nice backdrop to this telescope. At first, the Europeans were going to build something. The scientists proposed something that they call the OWL telescope, OWL. And they wanted to be 100 meters in diameter, effective.
Holy cow.
Yeah. And so do you know what OWL stood for?
Uh-uh.
Overwhelmingly Large Telescope.
Of course it did.
And so the governing bodies, because this is a collective whole of Europe, the various countries, that are part of ESO, they looked at it and said, well, essentially, why don't you downsize that a little bit and try to build a large mirror, or, nowadays it's usually smaller mirrors that are put together like a jigsaw puzzle, mosaic type of pattern. Try to develop the technology to build a smaller one before you jump to the 100 meter. Because essentially this is an optical telescope, by the way. The largest optical telescope that the Europeans are operating now are the very large telescopes.
Right.
So these are on a little over 8 meters in diameter, and there is one mainly owned by Spain, and Mexico has a large share of it. That is the largest optical telescope that's in the Canary Islands. That's a little over 10 meters in diameter. It's a little larger than the Keck telescopes that the United States have in Hawaii and the Big Island, top of Mauna Kea. But yeah, so the European government said, okay, we'll give you less money, but you need to build a smaller telescope. Well, at the time, the Europeans knew that the United States were building 2 other telescopes. There's the giant Magellan telescope, and they had proposed to build the 30-meter telescope. Now, the 30-meter telescope, you don't have to ask what's the diameter of that mirror.
Right,
30 meters. So if you're going to build a telescope, you want to beat the Americans, so you have to make it larger than 30 meters in diameter, so they opted for 39 meters.
It's like an arms race.
Yes. I mean, there's something in astronomy. It's a disease. It's called aperture fever.
Yes.
And it really means as when you purchase a telescope, let's say you obtain one Christmas time as a young child. And let's say it's of a certain size, maybe your parents, Santa spent on the order of, let's say, I don't know, $100 to purchase the telescope for you, to make the telescope at his workshop in the North Pole.
Right.
And then the year you use it, and that's fine. Remember the rule of thumb, Robert, anytime you buy a new telescope, you're guaranteed it's going to be cloudy at your location for about 2 weeks.
At least 2 weeks.
Yeah. And so by the time, around New Year's, when you're able to use your telescope, and then from there forward, it comes to a point where you're like, I really would like to have an even larger telescope. Jupiter looks really cool through my telescope. Saturn looks really cool. All my friends and family have looked through it. And wouldn't it look better with a larger telescope? So the following Christmas, you put it on your wish list. Could I have another telescope? Of course, make it larger this time.
Right.
That's the aperture fever. You want a larger and larger telescope. It's nonstop.
That's it.
Now, Robert, why would scientists, why are they able, I should say, go to their governments and say, could you please give us billions of euros when you talk about the large telescope that Europe is building in the process of building. By the way, that slide showed it's now half built. So at the end of June, the extremely large telescope, the 39-meter telescope, is 50% completed.
Oh, nice.
Okay, so it's halfway there. So in a few years from now, you're going to be hearing lots coming from this telescope.
Cool.
But obviously they had to sell it to the government. In other words, the people.
Right.
Right? They had to sell the idea that, hey, we want to build this telescope, give us the money. The money, it's a lot of money.
It is.
So there are other things you can do with that money. But why build a large telescope? Why aperture fever? Why does having a larger and larger telescope give you something positive? And we're talking about, in astronomy in general. And it's not just optical astronomy. You could talk about the size of a radio telescope.
A radio
telescope. It works
telescope.
the same way.
It works the same
well.
thing, yeah.
Now, there are 2 main reasons why you want a larger telescope, a larger diameter. Robert, could you think of what are the main reasons?
Well, one of the biggest ones is you can see dimmer objects.
Right. In astronomy, we call that, do you remember? Starts with L. LGA.
I mean,
Light
gathering ability.
Light gathering ability.
Okay, I've never heard it expressed that way.
Yes, light gathering ability. And light gathering ability is directly related to the area of the primary element that's in your telescope. That would be a mirror for a reflecting type of telescope, or it could be a lens for a refracting type of telescope.
Remember, folks, from your geometry class in high school, the area of a circle goes up as pi r squared, right? So if I double the diameter, I've got 4 times the area that's collecting light. So yeah, this is why any size telescope can see better than your eye. Your eye has a diameter of roughly 5 millimeters. So that's pretty tiny.
Right. So you could take, let's say, a reflecting telescope that has a mirror that's 1 meter across, an optical telescope, and you could calculate the light gathering ability. And then let's look at another telescope that's identical, except it has a 3-meter diameter mirror. If you're comparing the light gathering ability, you take the 3-meter telescope, right?
Square it.
3 times 3 is 9. 1 squared is 1. So that means the 3-meter diameter telescope has 9 times the light gathering ability compared to a 1-meter diameter telescope, everything else being identical. So the light gathering ability goes like the area. The larger the area, the more light that we can collect. In fact, when you first learn about telescopes and their optical properties in astronomy, you can think of a telescope as a light bucket. You think of a bucket that's used to collect rain.
Yep.
And you know that for a given rainstorm that you might have, the larger the size of the opening of the bucket, the more water you can collect, because the opening is spread over a larger area. It's going to collect more water droplets per second or per minute, whatever time you want to think about. Well, the telescope is the same way, except water. We're not collecting water, obviously, droplets of water. We're collecting photons, particles of light. And so the larger that mirror in terms of its area, the more photons we can gather per second of time. And that allows us to see fainter objects.
Fainter objects.
And a nice way to compare that is if we're in the optical looking and we compare what the Hubble Space Telescope can see. Now that has a mirror that's about 2.4 meters across. And you might say, why didn't we make it with 20 meters across? Or maybe like the extremely large telescope, why isn't it 39 meters across? And the reason for that is that the Hubble Space Telescope had to fit inside the cargo bay of the space shuttle. That's how it was put into space. So if you made it too big, it wouldn't fit.
It wouldn't fit.
And the James Webb Telescope is about 6.5 meters in diameter. We did not use the Hubble to put it up because the Hubble, of course, is done. It's in museums or museum pieces.
You mean the shuttle?
Oh, sorry, the shuttle is museum pieces. The Hubble will be there if we can get it back, right. In the museum. The shuttle, the surviving shuttles
are museum pieces.
And so they weren't available to put up the James Webb Space Telescope. In fact, we put it on an unmanned rocket, but we wanted the mirror to be bigger. Even if we had the shuttle around, if we didn't change the way the mirror was configured, it would still be limited by the size of the cargo bay.
Right.
But for the James Webb, we designed it like an umbrella, essentially. Not quite like that.
Popped open.
So it would pop open once it got into space. So it's in its compact positioning, it was small, and then once it got into space, it opened up to have a much larger mirror.
I will say this, if you haven't looked into it, look at the engineering marvel that is the unfolding of the James Webb Space Telescope. Over 400 operations, I think it is, total had to go right. So
yeah, and a lot of those are mechanical motions, and anytime you have anything mechanically designed that have lots of things that can go wrong mechanically, that increases the chance of something going wrong.
Right.
And so it was amazing that nothing went wrong, at least nothing that couldn't be fixed.
There were a couple of things that did go wrong, but they were fixable.
Fixable, yes. So there was enough flexibility built into the system that allowed it to overcome those issues.
Yep. It was brilliant.
Yeah. So what we have on the ground, if you look at the Keck telescope, that's 10 meters in diameter, the optical telescope. It can see things that are a lot fainter than the Hubble Space Telescope.
Right.
Why? Because it's on the ground with a much larger mirror.
So it can collect more light.
Yeah, so its light gathering ability is many times greater than the Hubble Space Telescope.
So
now,
why would you use Hubble then?
Yeah, so must be another advantage, right, of using a larger mirror, and that advantage is related to why you would use the Hubble. There's actually two additional reasons for the Hubble. Number one, because it's in space, it doesn't have to look through the blurring effect of the Earth's atmosphere.
That blurring effect is the big thing.
Yes, it gets a very sharp, high-resolution, crystal-clear view of the heavens compared to if you had the Hubble sitting on the ground looking up through the atmosphere.
Everything would be blurry and jiggly.
Yeah, so an analogy like this, if you can think about it, is imagine you're laying at the bottom of a swimming pool in the summertime, just for a few seconds looking up through the water, and there's somebody looking down at you at the edge of the swimming pool, trying to yell at you, why are you laying at the bottom of the swimming pool? This kind of thing. And they look blurry because the light is passing through the water. Obviously, light has to come down through the water, enter your eye, and then you're seeing the light, the image you're seeing having to pass through the water that's moving around, and it gets smeared out the image, so the person looks blurry. Now, if you compare it to, let's say you're laying at the bottom of a swimming pool, and it has no water in it, and the same person is perched over on the edge looking down at you saying, why are you laying in the bottom of a swimming pool when it has no water in it? The view that you get is going to be much sharper compared to when you look through the water.
Yep.
That's kind of the analogy here of looking through the Earth's atmosphere versus being out in the space with the same telescope.
Yep.
So there's the advantage of the Hubble. It can't collect as much light as larger telescopes on the ground, but its resolution is superior.
Because it doesn't have that blurry atmosphere to
And
look through.
it doesn't have that blurry atmosphere. And the other effect is our atmosphere acts like a shield. It blocks most electromagnetic radiation, most light coming from various sources in the sky from reaching the ground. For example, it blocks all the X-rays from reaching the ground. It blocks all the gamma rays from reaching the ground. It blocks a lot of the infrared. It blocks a lot of the ultraviolet. It even blocks very long wavelength radio waves don't make it to the ground.
Right.
So it acts like a shield. And that shield, depending on the region that you're looking at in terms of wavelength or frequency, what we say part of the electromagnetic spectrum, could block all of it or part of that light that's entering our atmosphere, trying to make its way to the ground. So if you have a telescope like the Hubble that's observing, let's say, in the far infrared or observing in the ultraviolet, a lot more of the photons will reach that mirror if the telescope's in space compared to the identical telescope being on the ground, looking at the same objects.
And that's why we want the Hubble. So getting back to the original topic, though, why do we want a larger mirror, though? What's the second reason for that?
So the second reason is based on the ability to see in terms of resolution. The larger the mirror, the smaller is what we call in physics the diffraction limit of an instrument. And the diffraction limit is how well you can see details. Now, a good way of thinking about it is imagine you're looking at a car at nighttime in the far distance. And let's say the car has two headlights that are shining towards you. But you know from experience, if you've been in a location where a car can be very far away from you at night, approaching you, and yet you can, when you look at it, it looks like there's only one headlight. It could also be a motorcycle, for far as you know, right, at that great distance. You don't really even know it's actually a car with two headlights. Or it could be a car with one headlight that's blowing.
Right.
And so it only has one working headlight. But a car can be so far away that the two sources of light merge together to look like one. Now, the ability to split those two sources of light, to tell they're two independent sources of light, is related to this diffraction limit of the telescope. And that's related to how large the diameter of the telescope is. The larger the diameter, the closer those two sources of light can be and still barely be able to tell they're two independent sources of light. If they were a little bit closer together, you wouldn't be able to tell that.
Or the farther away they can be. And you can
still tell they're two. So if you're looking in space and let's say you're examining a star cluster where stars are really close together, if you have a telescope with a much lower diffraction limit, that means the stars can be closer together compared to another telescope, and you can still tell there are separate stars, not one star.
Right.
Now, this is important for science. So here's one example. One of the things we like to do in astronomy is to measure the mass of stars.
Mm-hmm.
So there have been speculations that we found a star that seems to be more massive than any other star that's out there. In fact, let's say it's about 10 times more massive than what we think the upper mass limit to be. Not upper mass limit, nobody knows precisely. It's not something you can calculate from first principles. Let's say it's on the order of roughly 100 solar masses for the sake of this podcast. So somebody would report, I discovered a 1,000 solar mass star. So it's 1,000 times the mass of our sun, or 10 times more massive than this upper mass limit. So that catches people's attention. So they turn other telescopes, other instruments towards the star. And in most cases, what has happened is when they turn a large telescope towards that star, instead of seeing one star, they see several stars.
Right.
It's just that the instrument, the scientists that report the discovery, had too large of a diffraction limit. So they thought it was one star. But using a smaller diffraction limit telescope, one that operates at a much higher resolution, you could actually tell maybe there were 20 stars.
Right.
Right? So each star would have like 50 solar masses, which is well within the range of possibility of the masses that the stars have. There's nothing unusual about that. So having a high-resolution instrument, that is a telescope with a low diffraction limit, which comes from the fact of having a large diameter, that really can impact the science you have.
Right.
The other thing is, when you talk about radio astronomy, the resolution that you can see with a telescope is not only affected by the diameter of the telescope, it's also affected by what wavelength you're looking at.
Yes.
The longer the wavelength, the higher will be the diffraction limit, the poorer the resolution.
Right. That's one of the reasons why JWST had to be so much larger than Hubble, because to get the same diffraction limit, it was looking at longer wavelengths in infrared, so it had to have a larger diameter to get the same resolution.
Right, and plus the light gathering ability, we want to see galaxies that are newly forming. They're going to be extremely faint. In fact, the Hubble can't see newly forming galaxies at very high redshift, very high large distances away from us. And so if you think of radio astronomy, by their very nature, they're collecting radio photons. They have very long wavelengths. We're talking centimeters to even meters, depending on which part of the band, the electromagnetic spectrum you want to look at in the radio part. And so for radio astronomy, because the wavelength is so much greater compared to optical wavelengths, their diffraction limit is going to be very large compared to an optical telescope. That is, the resolution is going to be very poor. So in radio observations of some object, you might see a blob in space. With an optical telescope, you could tell there's 50 different objects there, but with a radio telescope, you see a single blob.
Right.
So you don't know where the radio waves are actually coming from because of that.
Yep.
So to get around that effect, even if you built a very large radio telescope, the resolution is still quite poor. To get around that, what they use is a very interesting technique called interferometry. And they combine signals taken from multiple radio telescopes, and it acts like one giant telescope that has a diameter that is equivalent to how far away the telescopes are spread out when they're making their observation. In fact, we've talked about this in past podcasts, that the Event Horizon Telescope was able to image the supermassive black hole that's both one at the center of our Milky Way and the imaged one at the center of M87. And the only way they could barely resolve that, you're looking at something very, very small in angular size, is they had to use telescopes spread over essentially the size of the Earth.
So using interferometry, they had the effect of a singular radio telescope that had a diameter roughly half of the Earth.
Yeah, or even close to the size of the Earth in terms of its diameter, when they're spread over far enough. And so in terms of resolution, they were able to increase the effective diameter, and therefore if you actually calculate the diffraction limit of a telescope, it goes like the wavelength divided by the diameter. So if you make the diameter very large, that overall ratio then becomes very small. So that means very high resolution in that sense.
Yep.
The only problem with that technique is you lose the light gathering ability because it doesn't operate like an effective telescope with the same size as the Earth's diameter.
I like to think of it as you've got a lot of holes in your big telescope.
Yeah. And of course, it's much cheaper to build, 7 radio telescopes spread over the Earth
than it is
to have one radio telescope
the
the size of the Earth. Right? That would cost a lot of money. I don't think,
I don't think anybody wants to pay for that one.
No, that would be a little bit expensive. In fact, and you wouldn't be able to build it on the Earth to be impractical.
Yeah.
I would collapse, and people wouldn't allow you to have such a large device sitting somewhere on the Earth.
Well, it'd suck to be whoever lived underneath it,
Yeah, well, gravity would have a major effect too. So So putting something like that in space would be the way to go.
Yeah.
To make a very large radio or collecting.
So are you making a proposal?
Well, if you send us the money, we would start working on the designs and the concept and propose that to space agencies around the world. And of course, nowadays we're not just limited to NASA. We can go to SpaceX and say, hey, we have money. Would you like to send this in space? It would take 10,000 rockets, but we could get all the parts up there or whatever, right? But money, if you got the money, Robert.
If you got the money.
You got the money. That's what we need.
We need Bruce Wayne.
So these large telescopes then coming downstream, including the extremely large telescope by ESO, are going to be very important for the progress of astronomy in the next several decades. So we're going to see a lot of interesting results coming from these type of telescopes. So that's the reason why people, governments as well as private donations, think it's worthwhile to spend, $1 billion on these telescopes. Is because the ability to see fainter and the ability to have much higher resolution than what a smaller telescope would provide.
And don't forget, those advances in engineering techniques and architecture techniques that go into building such a large telescope pay dividends in other areas as well. So
And
there's reasons they can be talked into building these things.
And you might say, well, put them in space. It's very expensive to put the James Webb Space Telescope that's about 6.5 meters in diameter into space. Imagine how much it would cost to put the 39-meter telescope in space.
Oh, Lord. That
So
would take, about 5 launches.
it's a lot more,
Yeah.
and a lot more things can go wrong. It's a lot more expensive to put up these very large telescopes in space and to have them on the ground. It's not like we're against that in astronomy. We would prefer that it be in space. So certain individuals, which I won't mention on this podcast, have said, oh, just put your telescopes in space, you astronomers. Why are they on the ground anyways? Because it's extremely expensive to putting them into space, and we rely mostly on government money.
And I would no, never mind.
Well, I was going to say, if some billionaire out there would like to donate money towards this, I'm sure astronomers would be happy to put their telescopes in space.
Love to donate the rockets.
Well, if we had our telescopes in space, we get above the blocking effect of the Earth's atmosphere. We get away from the light pollution.
And we'd get away from satellites getting in
We
the
get
way.
from satellites in near Earth orbit. Just put our telescope way out there. I mean, it's a better. And for radio telescopes, we want to get away from the interference that we release here on the Earth, terrestrial sources. So you want to put your telescope in space. In fact, there are a lot of studies that have been done and more sort of work recently, I noticed, on using the far side of the moon or the back side of the moon as a place to put a radio telescope. The problem there is that if there's nothing on the back side of the moon, that works really well. But now people are wanting to explore the far side of the moon, the back side of the moon. And when they do that, let's say you had a rover, which certain country has done already, they always you have to put a satellite in orbit around the moon, so relay those signals back to Earth. But if you're relaying signals on radio frequency, there is interference that can disturb your radio telescope. So, and probably is going to become more of a problem in the future.
Yes.
And so if I was to put up a radio telescope and go through this process of developing something, of raising the money to pay for it all, and to put it in space, I would not put it on the far side of the moon. I'm sorry. I would put it way out in the space.
Yep.
Have it on its own independent orbit around the sun, that gradually the telescope moves away from the Earth, that you're not going to be affected too much by stray signals coming from the Earth. I think that's going to end up being the best place to put it.
I can't disagree.
But that's for the far future.
Yeah.
Well, hopefully, it'll be like within 50 years, but who knows, right? It's like anybody who predicts the future. I mean, if you get it right exactly, it's really just coincidence.
It is.
Right? No one can really predict the future exactly. So, So that was the big news about what's happening here on the Earth. The other big news that happened recently that you may or may not have caught wind of is a paper that has been accepted by the monthly notices of the Royal Astronomical Society. And Robert, you want to pull up slide number 2, please?
There it is.
This paper, then, as you can read the title, says JWST Early Universe Observations and Lambda CDM Cosmology. Now, let's parse through the title. Okay, so it's been accepted by the monthly notices of the Royal Astronomical Society. This is the abstract and title and author. It's by Gupta, who is an adjunct professor at the University of Ottawa in Canada. This paper has been published by now, certainly. I just haven't pulled up the published paper version of the abstract. This is the accepted one. Now, the title says JWST, Early Universe Observations. Now, we've covered this on this podcast also in the past about the fact that JWST, one of the discoveries that came out with the observations that were taken roughly a year ago, the first set of observations, is that they detected a lot of massive galaxies at an early time in the history of the universe.
Right.
That is, we're detecting galaxies that literally existed roughly 300 to 350 million years after the beginning of our universe, after the Big Bang, as we'd say.
Mm-hmm.
Okay. Now, a lot of people had problems with this because it takes time to form a galaxy.
It takes time to form stars.
And galaxies are formed, of course, of stars. So where does this structure comes from? That's right. First thing we should explain. If we lived in a universe in which the matter was completely evenly distributed everywhere. Now, the techno phrase that we use for that is that the universe is both homogeneous and isotropic. Now, what those fancy words just means, that if I was at a position and I was seeing light coming from me isotropically distributed, that means in every direction I look, all around me, above me, below me, and all around my sides, 360 degrees, all around everywhere, I get the same amount of light coming towards me. That's perfectly isotropically distributed. That's what that means. Okay? Homogeneous means it doesn't matter where I am in the universe, everything would look the same. So if we think we live in a universe that's essentially isotropic and homogeneous, which means it doesn't matter where you are in the universe, when you looked around at very long length scales over a large swath of the universe, everything would look statistically the same as any other location you could make those observations.
And notice that word. It's not specifically the same, it is statistically the same.
Right, because you know it doesn't apply locally, right? We're standing on the Earth. If I look down towards the Earth, that is not the same view I get as I look away from the Earth out into space. Right. But over very large length scale, the distribution of galaxies that we're seeing then looks roughly the same in all directions statistically on average. Anyways, that's a fundamental tenet and the use of our best laws of physics that we have to describe gravity. And that's Einstein's general theory of relativity. A major tenet in that is that the universe is isotropic and homogeneous, the cosmological principle, as we call it. If you make that assumption, then you can solve essentially Einstein's general relativity, what we call the Einstein field equations, and apply it to the universe as a whole. Okay? When we do that, we know that if the universe was completely isotropic and homogeneous, it is hard to imagine where the structure comes from that we see around us. Where do the galaxies come from? Where do the stars that make up the galaxies come from? Because if there are no density enhancements anywhere, there is no region where gravity would do its thing and draw in surrounding material from underdense regions to ultimately collapse things via gravity and to form stars and then ultimately systems of stars like star clusters and galaxies and so on. Right. So you need what we call anisotropies, another fancy word, anisotropies in the very early universe. That is, you need to have regions in the universe that had slightly higher density than other regions in the universe in order for gravity to do its thing, to form the structure we see around us today. Now, the big question is, where does those anisotropies, those density variations, come from? Now, it's very technical, but it involves the use of, today, if we think about cosmology and inflation, which is the early exponential expansion of the universe. It's not the dark energy that we talked about. This is very early on, like 10 to the minus 34 seconds after the universe began. There are things in quantum mechanics called fluctuations. Rob, do you want to say a little bit about what quantum fluctuations are, very briefly and simply?
Very briefly and succinctly is about all I can speak on them, and that is basically stuff can pop into existence and fade out as long as, the more energy involved, the shorter the time they can exist. So you can basically have...
And what's that fundamental principle in quantum mechanics that describes all of that?
Oh, well, that's the uncertainty principle.
Yeah, the Heisenberg uncertainty principle.
Yeah, so basically, as you can have a lot of energy just suddenly appear, but it has to disappear very quickly. Or you can have a little bit of energy appear, and it can linger around for a while.
Right.
And these are not just suppositions. We've actually measured and seen these effects. So this stuff happens.
Right. So when you first learn about the Heisenberg uncertainty principle, it's usually referring to you can't measure with infinite precision both the location and the momentum of a particle.
In other words, I'll clarify it a little bit and go, you can't know where something is with absolute precision and with the same level of precision know how it's moving.
Yes.
You can know one or the other. You can know where it is or you know how it's moving.
Right. And that also refers to, as you mentioned, Robert, energy and time.
Right.
So if you look at, how does that relate to what we're talking about today? Well, here's how it relates. Imagine that you took a box of space, the vacuum of space, and in that box there happens to be nothing. There are no particles, there's no hydrogen atoms, there's no dark matter particles, there's nothing in that box. But what we know that can be in that box are fields. And this comes from a part of physics known as quantum field theory. So what quantum field theory does in a nutshell is unites quantum mechanics with relativity. And it describes that the existence of particles like electrons is really a field. And you can think of that field being described from quantum mechanics. So if you've taken quantum mechanics at university, then you can think of the Schrodinger's equation and the wave function, these kind of things. So you can think of these energy fields, for lack of a term that I don't want to get too complicated here, that exist or permeate all through space, each field representing every single particle. So for the proton, there would be a proton field. But technically, we know protons consist of 3 quarks, so there would be a field for each of the quarks.
Right.
You can think of it that way. Now, out of the vacuum of space, there can be energy fields that exist for a brief period of time and then go away, and it doesn't violate any known laws of physics because things happen so quickly.
Right.
It doesn't violate the uncertainty principle of quantum mechanics. So are these fluctuating, changing fields, right, that exist any part of space, all around us. It gives rise to the notion, if you want to look into it more detailed later, things that we call virtual particles. There are real particles and virtual particles. Virtual particles exist for a fleeting moment of time and then disappear.
Right.
And real particles hang around for a lot more.
For a lot longer.
Depending on the particle, could be around for billions of years, right?
Right.
And so that means that in the very early universe, there were these quantum fluctuations, and those quantum fluctuations, due to the appearance of these energy fields and then disappearance again, and like this boiling, teething froth of energy in the vacuum of space. And this gives rise, during inflation, these length scales, which are very, very tiny. You're talking very small, Planck-like length, for those of you who are more into physics part of things. Go look up the Planck length. They're very, very tiny measurements, right? It's like 10 to the minus 32 meters or some of that order. I forget the exact number now with the Planck length. And these lengths, type of fluctuations of those length scales during inflation, because the universe inflates so much so, something the size of an orange blows up to be larger than the solar system. These quantum fluctuations expand out greatly and becomes macroscopic in size because they increase so dramatically in length scale. So these quantum fluctuations are the seeds of structure formation in our universe via the cosmic inflation type of scenario.
And I'm going to bring up something, on these quantum fluctuations, if you want to look at a macro, an observable level of these events, look up the idea of rogue waves, because they do much the same thing. You get one wave that essentially vampirizes, takes up the energy field of the rest of the waves in the area and combines it into one big massive wave, and it sinks ships.
Yeah, so these vacuum fluctuations then ultimately, as I said, act as seeds for the formation of structure because they are responsible for the anisotropies, the existence of these overdense regions through the universe. And what happens is when the universe cools down, gravity eventually can do its thing, and it can draw in the material into these overdense regions, ultimately forming things like stars and galaxies, as we've mentioned already. So that all requires time.
Right.
If you go back to the early point of the universe, where the universe is roughly about 400,000 years old, the temperature at that point has just fallen below 3,000 Kelvin, and hydrogen atoms can now form. They can live longer. Prior to that time, they would form, and then right away, there'd be a high-energy particle would break them apart. So statistically, you can't form them. But when it becomes cool enough, these structures can survive. And then ultimately, they would collect together and form galaxies. But all of this process of going from initial overdense regions, these vacuum fluctuations, to actually having galaxies, we thought that may require, I remember, people talking about it a couple decades ago, that would require 2-3 billion years for that to occur. And then we started finding galaxies at an earlier point in the universe. Light travels at a finite speed, so I can look at a galaxy that's 13 billion light years away. And when those photons enter my telescope tonight, they've been journeying through the universe for 13 billion years. I'm seeing the galaxy as it was 13 billion years ago, not as it is today.
Right.
So I can look at things in the early universe by looking at things that are very, very far away. When we started forming galaxies that were around just 2 billion years after the universe formed, clearly galaxy formation only required 2 billion years to do its thing. Then we started finding things that were only 1 billion years after the Big Bang. So clearly structured galaxies can form only after 1 billion years and so on. Well, with the James Webb Space Telescope, we can look back essentially at the era of galaxy formation, the epoch of when galaxies start to form. And we find in these early studies galaxies that are on the order of 300 to 350 million years old. So that's a dramatic shortening of the time we thought, not that long ago, in which we needed to form mature galaxies.
Right.
So it looks like we only need a few 100 million years. So that was the major discovery that was announced by people analyzing the James Webb Space Telescope data. And of course, people out there grabbed that and said, aha, the James Webb Space Telescope just proved the Big Bang Theory wrong, because out of that theory, the universe is about 13.8 billion years old, round that off to 14 billion years old. Clearly, you're forming galaxies too fast, so it must be a lot older than 14 billion years. So we just disproved the Big Bang. But of course, that's total nonsense. What we did is added some observational information to how galaxies formed. And in particular, what is the time scale? How long does it take for a galaxy to form? We don't need 3 billion years. Looks like we only need a few 100 million years for gravity to do its thing.
Yep.
So it affected galaxy formation, which was one of the major reasons to build the James Webb Space Telescope to begin with, but it doesn't say anything about cosmology, anything about the Big Bang or the age of the universe.
Right.
Now, this paper uses that information about the early timescales of the formation of galaxies along with the present understanding of our universe. So we know that our universe, and it comes from the title of the podcast, Cosmic Pi. What is the cosmic pi? The cosmic pi is a breakdown of all the matter and energy that makes up the universe, its composition. 70% of the universe is in the form of dark energy, which is responsible for the accelerated expansion of the universe. The other 25% is made up of dark matter, which explains why stars in the outer parts of galaxies can move so fast without flying away from the galaxy. There's extra matter that doesn't give off light in our galaxy and other galaxies.
Doesn't give it off or absorb it.
Right, or absorb it, that is found in most other galaxies. And so therefore the mass is a lot greater, and greater mass, more gravity you have to hang on to those fastly moving stars in the outskirts of galaxies. And so we know that dark matter makes up 25% of the universe, which leaves roughly 5% left over of the things that you and I are made up of, Robert, and anybody else who's seeing or viewing to this podcast, and so all the normal stuff like protons, neutrons, electrons, and so on. And so that type of universe is known as lambda, the Greek letter lambda, CDM. So lambda means dark energy, CDM stands for cold dark matter. So we live in a dark energy, dark matter type of universe. That's the formulism that best describes our present universe. It's called the concordance cosmology, the standard cosmology that we think applies to our universe today. And with that cosmology, with the values of the input of the parameters for this cosmology, we come up for the age of the universe based on how fast it's expanding. And it's about 14 billion years, like 13.8 billion years old. Now, what this paper proposes, like I said, this paper has been accepted and probably is on the verge of, if not already, has been published now. This paper proposes that the universe is actually 26.7 billion years old. And because it's almost double the age of what the standard cosmology says it should be today, there has been lots of time for galaxies to form. So to find galaxies that are nearly 13.8 billion light years away is no big deal, because the universe has been around not for 14 billion years, but it's been around for almost 27 billion years.
Right.
Now, Robert, there's a problem with that.
I'm just thinking of Carl Sagan and going, extraordinary claims require extraordinary evidence. So,
Well, the three major themes of this paper is it's based on this conclusion on something that we call tired light, along with the expanding universe and the changing of fundamental physical constants in nature, like capital G, the Newtonian gravitational constant. Those values have to change for this model to work. So this model was designed to show that these early results from the James Webb Space Telescope can be incorporated naturally into a much older universe. Instead of fooling around with galaxy formation and make the changes there, the author decided to make changes on the cosmology, which the results really didn't say anything about.
right.
So it's a weird type of situation. Personally, I don't know how this paper was ever accepted for publication. If you want to get things going and debate and look at it in science, that's what we do, then I can understand why it was published from that point of view. But there's been a lot of evidence that shows the universe then is not
27 billion years
yeah,
old.
27 billion years old. We know the tired light idea. What's the tired light idea? Is that light photons lose energy over time. So photons then are not redshifted because of the expanding universe. They lose energy, and a lower energy photon then will go to longer wavelength.
Would look redder.
Yeah, so in the vacuum of space, photons would naturally lose energy. Well, that would disturb the momentum, and observations that we make of light that we receive, including light from the leftover heat from the Big Bang, the cosmic microwave background, would actually not work if the tired light scenario is valid.
The bottom line, where does the momentum loss go? Where did that momentum go? Where did that energy go that was lost? And things like this.
Now, the tired light idea, that was proposed way back in the 1930s, like 1935 by Fred Zwicky. And people have looked at this over and over and over and over again, and there's been absolutely no evidence of this. The twist here for the author of this paper was to use tired light in an expanding universe. Well, expanding universe was known since the late 1920s. 1929, Hubble publishes a paper regarding what we nowadays call the Hubble law, the fact that galaxies further away travel faster away from us, greater recessional velocity, have a higher redshift, as we say in astronomy. So that was evidence of the expanding universe. But in 1935, when the tired light idea was introduced, people have looked at it since then, almost 100 years now, and there's no evidence of it, even in an expanding universe. So that's why there's a third piece that you need to do is have changing constants. Now, very, very famous physicist Paul Dirac mentioned this I believe it was the 1960s when he first mentioned the possibility that constants of natures can change and so on. And we're going to say more about it a little bit later.
Okay.
But the slide that you're seeing before you is measurements of the temperature angular power spectrum. Now, that's a lot of words there. What does that mean? What it means is to measure then how things are correlated, in this case, temperature variations at different angular scales in the universe. So we can measure the leftover temperature of the Big Bang. It's roughly 2.7 Kelvin today. And with measurements like different satellites we put in space, in particular the Planck satellite, which is what this data is from, Planck from the 2018 paper, we can measure then over different angular scales in the sky how the temperature varies. Now, the temperature varies on the order of like 1 part in 100,000. So that means if you look in one direction in the sky and measure the leftover heat from Big Bang, you measure its temperature. If you look in the opposite direction, you get almost the same temperature to 1 part in 100,000. Now, why is that important? Why don't you say it's the same temperature? If the universe was completely isotropic and homogeneous, there were no overdensities, it would have exactly the same temperature everywhere.
Right.
But because it doesn't, and we're measuring the leftover heat approximately 400,000 years after the Big Bang, because the temperature is not precisely the same everywhere, there must have been overdensities and underdensities in the universe and the distribution of matter. And remember, as we mentioned, that came from vacuum fluctuations during the inflationary epoch of the universe. That gives rise to structure. It gave rise to galaxies, including us and stars and so on. So we want those anisotropies to be there in the distribution of temperature across the sky. What this power spectrum measures is the amplitude of these differences in the temperature at different angular scales. How well are they clustered together statistically? So we can measure the separation, let's say, of 90 degrees from each other, 2 points. Or we can measure pair of points that are separated by 1 degree and measure those pairs all over the sky so you have a large number of pairs, looking at the differences in those temperature measurements to get this amplitude that you see here. Now, the funny bumps and wiggles is related to the cosmology, the fact that the universe is 13.8 billion years old, the fact that it has a dark matter component, and so on and so forth. If you were to adjust cosmology, so now the age of the universe should be 26.7 billion years old, it would not match up what we see here. By the way, the data points from the Planck satellite are the red data points. The cosmology that we use, that lambda CDM type of cosmology with amount of dark energy and dark matter and normal matter, is the blue curve you see, and it perfectly matches the data
that's
points.
A pretty close match.
It's a very, 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 very close match.
Yep.
And so if you were to change the age of the universe, that blue curve would be different than the data points. It would be somewhere else. And so you'd have a complete breakdown in the match of standard cosmology with the measurement of the cosmic microwave background radiation, this so-called power spectrum. But there's more than that. If you go to slide number 3, Robert, slide number 4, one of the things we can do in astronomy is we can age objects. We can determine their age. So on Earth, we use radioactive nuclei in rocks and stuff to determine that the Earth is roughly 4.5 billion years old. But we can also date stars. And the way we date them is to use star clusters. So these are a collection of stars where you might have tens to hundreds to even up to 1 million stars all close together, gravitationally bound as a complete system. And these stars all formed at approximately the same time. Now, stars, when they evolve through their lives, the amount of time it takes the star to go through its different phases depends primarily on their mass. Mm-hmm. Massive stars go through all their life cycles a lot faster than a low-mass star. So what happens if you form stars in a star cluster, one star cluster that's roughly in the same location, is that you're going to form, let's say, a collection of, 100 stars. Those stars are all going to have different masses. Why? Well, why would you form all 100 stars that have precisely the same mass? There's no law in physics that would apply. You're going to have a range in masses of how these stars gravitationally collapse to form in the first place. So you form stars of various masses, all forming at roughly the same time. Well, the higher mass stars are going to go through all the different stages of their life, as I mentioned, faster than lower mass stars. So on the far left of this panel, we see what we call the HR diagram. This is a plot essentially of temperature increasing to the left, the luminosity, or if you like, the wattage of the stars increasing upwards. And that dotted line that we see here that stretches diagonally from the upper left to the lower right, that's known as the main sequence. When a star is on that region of the Hertzsprung-Russell diagram, it is happily converting hydrogen to helium in its core. Mm-hmm. But eventually the hydrogen runs out. The fuel source is gone in the center. The star moves off of that main sequence, as we call it. And that's what's happening in the middle panel. Some of the higher mass stars have moved off that diagonal line. Now they've left the main sequence. And the most massive star that's still on the main sequence, that's ready to move off, it's its turn next to evolve off the main sequence, we call the turn-off point. And if you look at the panel on the far right, notice more time has elapsed, so even lower mass stars now are at the turn-off point. So knowing precisely what is the mass of a star at the turn-off point, we can come up with an approximate age for that star cluster. For example, the Sun has a total main sequence lifetime of 10 billion years. If a star identical to our Sun with the same mass then was at the turn-off point, that means it's ready to move off the main sequence. It is just completing hydrogen fusion in its core. And that means 10 billion years have elapsed since its form. That star cluster must be 10 billion years old. Now, we can look at star clusters that are really old to try to estimate their ages. So this, on the next slide, is an image of one of these star clusters that's known as a globular star cluster. This is a beautiful image taken with the Hubble Space Telescope. And here you can see the high resolution effect coming into play. You can see the differences between stars quite dramatically until you get to the very center of the star cluster.
Looks a lot better than the ground-based images
I've
taken.
Better. Now this globular cluster M2 has nearly 1 million stars in the cluster. And when we look at the HR diagram of these type of star clusters, like the one you see here on the next slide, we can look at where the turnoff point is. And by noting at where the turnoff point is, we can determine what is the age of these globular clusters. And what we discovered was that the ages of these globular clusters, the oldest ones, are on the order of about 13 billion years old.
In other words, the age we think the universe is.
Yeah, so if the universe was 26.7 billion years old, where are the old globular clusters that are 15 billion years old, that are 20 billion years old, that are 23 billion years old? Where are they? We can't see them. And they should be around us. We are part of the universe, so even old things should be around us today if they have survived since the early time of the universe. So none of the globular clusters that we see close enough that we could measure their HR diagrams have any ages at all old enough to be consistent with this model.
Okay.
The second major part of this model is the fact that these physical constants of nature should change with time. Well, let's look at the big one, the gravitational constant, the capital G. We have put precise constraints, very tight uncertainties or error boxes on how much G can vary, and so that we wouldn't be able to detect the variation of capital G. And this is the latest, greatest paper that I could find. This was published in 2019. And it says that the value of G has not changed by roughly 1 times 10 to the minus 12 of its value per year.
So decimal point, 11 zeros, and a 1.
And then a 1. In other words, as far as we can tell, G is an absolute constant to very high precision. And this, by the way, is based on seismology of stars called astroseismology, how they shake and so on. We have the techniques were invented several decades ago, and they have matured enough that we can put these type of constraints. So there is no evidence at all that shows that these physical constants of nature, G is just one example, have changed with time. That is not consistent with this paper. So Robert, as far as I can tell, there is no evidence at all that supports the universe is 26.7 billion years old. It doesn't work.
And again, making an extraordinary claim, you better have extraordinary evidence. And as we're pointing out, as Wayne has pointed out, there's no evidence.
So this paper belongs in the trash bin of history as far as I'm concerned personally.
Right.
But it's fun to go through.
It's fun to go through all of it, though, but yeah.
And that's how science works, right? It gets tested, it gets double checked and triple checked, and if there's something wrong, somebody will find that out eventually, and then you get rid of it or you modify things. And it's the same case here. Publish it, why? So we can look at it and see if there's anything wrong. Poke holes in the ideas, and if there's something wrong, then it needs to be rejected or modified.
This is why I've told many of my friends that if you're going into science, don't have an ego, because it'll be all kinds of holes poked into it professionally.
Exactly. Now, Robert, we're at the end of the podcast, unfortunately. So if you're interested in science, if you like to, poke holes through other people's papers, including Robert and I's papers, you're free to do that. If you want to learn more about science, to become more efficient at that type of process, then come to the University of North Dakota, take classes, join up the degree programs here. If you don't want to do that, if you like to just do online type of courses, we have, of course, an ability to allow you to take online programs. You can look up und.edu/online to look at all the different types of information that they have on that website that allow you to take courses from afar. But of course, if you're local, please stop in to visit Robert and I. We'd be happy to see you.
Or if you'd like to be local, come see us.
Exactly. And maybe you'll be a guest on our podcast and we can discuss things. That would be kind of neat. Now, the next podcast would be next Tuesday on August the 1st at the same time, 3 p.m. Central Daylight Time. We always leave you with a quote, Robert, at the end of the podcast. Since we talked a lot today about cosmology, it's fitting that we would have a quote that's from a cosmologist, very famous cosmologist, who's unfortunately no longer with us, and that is Edwin Hubble. Can you think of a telescope that was named after him, Robert?
I can think of one. I think we mentioned it today.
Many times we mentioned it. So Edwin Hubble quoted, Equipped with his 5 senses, man explores the universe around him and calls the adventure science. Thank you for listening. If you like this podcast, don't forget to give us a thumbs up and subscribe.
All right. Have a good night, folks.